Hi, Dr. P here, and we're going to be moving on into chapter 15, looking at aromatic compounds. Now, I want to start off by examining the stability of benzene. And we'll take a look at this, both the experimental evidence for the stability of benzene, and then also we'll look at the explanations for the stability of benzene. So let's take a look here first at enthalpy of hydration, or sorry, hydrogenation. Let's take, for example, cyclohexene. If we hydrogenate it and make cyclohexane, our delta H naught here is around minus 120 kilojoules per mole. If we do the same thing with benzene, we would expect, so our delta H naught expected would be minus 360 kilojoules per mole. And if you're reading the text, you'll see that the values that are reported for the actual and expected are slightly different, but only slightly different. What is actually very different is the delta H naught actual is minus 208 kilojoules per mole. That means that we've got somewhere around 150 or 152 kilojoules per mole of stabilization energy. Sometimes this is referred to as resonance stabilization. Okay. So what other evidence do we have? So we've got our enthalpy of hydrogenation. So that's implying that, benzene has around 150 kilojoules per mole, or it is 150 kilojoules per mole more stable than we would expect. So something is going on here. Also, we can take a look at some reactions. In particular, we'll look at the bromination reaction. We get substitution, not addition. In fact, not only do we get substitution, but the reaction won't even occur unless we have a catalyst. So, taking again the example of cyclohexene, if we react this with Br2, we will get, of course, the addition of the bromine, the Br2 across the double bond, get the enantiomer as well. If we try that with benzene, we get no reaction. Now, we can get a reaction to occur with benzene if we do Br2 and use FeBr3, which is a Lewis acid catalyst. We'll look at this actual reaction in chapter 16. But we'll see that we actually get a substitution. We get one bromine on the ring, the hydrogen is removed from the ring, we get HBr as our byproduct here. So this is interesting. Benzene reacts in a much different way than a regular alkene does. So something is definitely going on. And one of the ways that we describe this, or perhaps even explain it, there are actually many ways, so maybe I'll go through a few of them. So let's ask the question, why is benzene so stable? And then what does aromatic mean? Put that in quotation marks. All right. So we can have a resonance picture where we have benzene. I'm going to go ahead and put in the hydrogens here. And I'll use a red arrow to indicate my electrons moving around here. And we could push electrons around and get a different resonance structure for benzene. So that double bond is there, that one is down there, that one's over there. Still have my hydrogens here. And I know, yes, it looks like it's just rotated 60 degrees, but remember with resonance structures, we're pretending that all of the atoms are fixed to the piece of paper here. So our double bonds are in different places then. These are resonance structures. And what this is actually kind of getting at is we have our electron density is delocalized over the ring. And that's why often people will draw benzene like so, the hexagon with a circle in the middle. And we would then represent it with a model like this guy here. Let me zoom out. Excuse me. And each of these black balls, of course, is a carbon. The white are hydrogen. And then we have our gray sigma bonds. And then our pi system is in pink and purple. So this is one p orbital here that contributes, these spheres here, that contribute to the pi system. So we've got 6 total p orbitals, and they all overlap and give us this pi system. So what it ends up looking like, if we were going to draw it out, is something like this. And then I could color these guys in here. I could do, like, let's say red and blue. We'll do red up here. And then we'll do blue on the bottom here. A little easier to see than just shaded and unshaded. And then we can see that we've got delocalization over the whole ring. So we've got this big cloud of electron density above and below the plane of our carbon atoms and our sigma system. And this actually leads to another version. And first I should call this the delocalization picture. And eventually this will lead us to something, or actually lead us to using molecular orbitals. And let me see if I can find my molecular orbitals here. We'll get a molecular orbital picture. And let me go ahead and let's see here. Let's do this. Okay. Now, before I draw these, I do have some diagrams. And this is from the Klein text. Let me zoom in a little bit here. There we go. And there are 6 molecular orbitals because there are 6 p orbitals and 6 pi electrons that contribute to the overall pi system. And again, the phases of the individual p orbitals will change. When they're all the same phase, we get this lowest energy orbital, pi 1, or they call it here psi 1. I'm going to call it pi 1, I'll label it, but I use the Greek letter psi here instead. And this is our lowest energy, no nodes other than the node in between the p, or the orbitals of the pi system. Then we have 2 orbitals of the same energy with 1 node. And then we have 2 orbitals with 2 nodes each, and then 1 orbital with 3 nodes. Okay, and there are mathematical reasons for how we get these. It's basically the way of combining our different orbitals. The picture from the McMurray text is drawn a little different. And so let me zoom in a little bit more here so you guys can see this. Put a light on here, see if that helps a little. All right. So look at these. Look at the lowest energy orbital. All of our constituent p orbitals have the same phase. Next up, we have 2 equivalent energy degenerate orbitals. One has a one has a node going this way, the other has a node along the middle intersecting 2 of the carbon atoms. And so we have no electron density there, and we have the phase change across the node. And then we can go higher up and see that we have higher energy orbitals with more nodes, and eventually a node between every orbital. And once again, we've got our 6 molecular orbitals, came from 6 atomic p orbitals. Half of them are bonding and half are non-bonding. And we have 2, 4, 6 pi electrons in our bonding orbitals. So that's going to explain the stability of our benzene. We don't have any electrons in the anti-bonding orbitals. So again, I may have misspoken. Lower energy 6, the half that are lower energy are bonding, the half that are higher energy are anti-bonding. Anything on the 0 of energy would be non-bonding. So we only have bonding orbitals that have electron density in them, that have electrons in them, I should say, and thus we get a nice stable bond. And it's the presence of this guy down here that really shows how stable they are. It's kind of like that lowest energy orbital with the conjugated dienes. This is our delocalized picture. This is our delocalized picture. Okay. Now I could draw this a little bit differently. I felt like I should explain several different ways or show you several different pictures. So we have, the big blobby things, which is a little more accurate to what they look like. We have the 3D or sort of side view 3D of the, let me zoom out again. We have this sort of side view 3D of the p orbitals, and then we can look top down. Okay, so this is going to be looking top down. All right, so we're going to have, so basically I'm looking at it like this, like that. Okay, so I'm going to draw circles for each of the p orbitals. And so what we'll have is we'll have all red circles here and the blue is going to be on the other side. So we've got all red phase here. And that's going to be our pi 1. Next we'll have pi 2 and pi 3. Let me draw those. And we're going to have nodes. We'll either have a node like that, or we'll have a node through there like that. And so one of these, we'll get that. And then our blue phase on the other side, those blue phases will be up. And then in the other one, we'll have our red on one side, and then a node, and then blue on the other. And remember, we're just looking at the top. We're looking top down here. It's another way of representing it, and it's a little easier to draw than this guy, because we're just looking at it top down. Then we can have pi 4 star. It should be a star there. So pi 4 star and pi 5 star, and then ultimately pi 6 star. So let me draw these in here. Now, do I expect you to draw these? Actually, no, I don't. I'm not going to ask you to draw these on a quiz or an exam. I do want you to understand that we have this basis for, this molecular orbital basis for the stability of benzene. So let's go ahead and put, we can put a couple of nodes here. We could have, let's see, we could have a node, we could have one there and one there. Or we could have one there and one there. So this would give us red there, blue there, blue there. And here we'd have, a blue there, and a blue there, blue there, blue there, and then red and red. And then lastly, we'll have, whoops, we're going to have all 3 nodes here. So we're going to have alternating red and blue phases. And so this is obviously contributes nothing whatsoever to bonding. It's totally anti-bonding. And then we'll fill in our electrons. 1, 2, 3, 4, 5, 6. Okay, and our 0 of energy is right there. So we'll say bonding orbitals occupied. And that means it is very stable. Zoom out just a little bit here so you can get the whole, a little bit more of the whole picture here. There we go. All right, so this is another representation. Again, we've got our resonance picture, our delocalization picture, and then our molecular orbital picture. And these all explain the stability of benzene. So the last thing I want to do in this video is just give you a initial definition of aromatic. Okay. Originally, back in the 1800s, aromatic compounds are, well, we'll just say smelly compounds. Related to benzene. Indeed, the term aromatic originally referred to the smell of benzene. Most of you probably have not smelled benzene. I'm actually not sure if I have or not. I had benzene as an unknown, as an undergrad in a lab, and I broke the NMR tube when I was cleaning things out, and I spilled a little bit on my hand, and it smelled kind of weird, like something I had never smelled before. It definitely did not smell like toluene. It smelled sweeter and less like a solvent. Hence the term aromatic. Our modern definition is going to be aromatic compounds are compounds that meet certain criteria to explain, or certain criteria that explain their extra stability. Like benzene. And in the next lecture video, we will look at what those criteria are. All right, so I'll leave you with that little preview there. Okay, well, until next time, stay safe out there. Bye now.